I'm Krishna. Before I start, I just wanted to know how many of us here are computer scientists, like we program, and data scientists or researchers? Okay. Anyone I'm missing? Business people, like just students? Okay. Awesome. And how many of us have built neural networks before? Built neural networks? Okay. Awesome. And how many of us don't know anything about machine learning? Like no idea. Okay, awesome. So I'm Krishna. I did my bachelor's in India, and I just finished my master's from University of Leon 2 and UPC. UPC is a university in Barcelona. I have around 3 years of experience as a data engineer, and I'm a Apache System ML committer. And that's me doing yoga, so I like doing yoga and machine learning. Yeah, so this is the agenda for today. First, I'll introduce what mixture of experts is, and then I will explain the intuition. Like, it's really hard to understand these abstract things, so I'll maybe try to give a good analogy. And then I'll show my results. So this work is my master thesis work, which I did the last 3 or 4 months at University Laval. And then I have some results, and we'll make some good conclusions based on the results. So before that, mixture of experts is not a new topic. It's a very old paper from 2002. So the first thing I had to do when I started my research internship was like read this paper, like with all this math, and yeah, and get this table exactly. So I had to read every parameter, everything, and try to replicate exactly how the authors had implemented, and then do little more experiments on it. So it was a very nice experience, and I would encourage everyone to maybe, if you want to get into research, read a paper and try to be exact about replicating the parameters. And sometimes they just skim over the details, like it's obvious, you know, so we will not talk about it. That's very, very usual. Okay, so this paper was introduced by Yoshua Bengio, Colabert. So they are leading researchers in machine learning, and this was accepted in NIPS 2002. So the problem was that SVMs don't scale well. SVM is an algorithm, and it has a quadratic runtime complexity. So when you have a lot of data points, it becomes super slow. So they showed a way where you could like use SVMs and scale it to more than 1 million data points. And this approach that they mentioned in this paper was very easily parallelizable, and so it's pretty cool. And this is also an ensembling technique where you can combine results of multiple machine learning algorithms, and they can obtain better predictive performance. So before we start, I just wanted to give you some kind of intuition. So for that, I want 3 volunteers. Woohoo, 3 volunteers? No one, please. It'll be fast. Yeah, awesome. Big hand for the volunteers. Ta-da. Okay, awesome. So what's your name?
Ismail.
Ismail?
Robert.
Robert?
Raymond.
Raymond, yeah. So awesome. So this is an interactive interactive session I wanted to have and try to make it fun. So you all have a surprise test tomorrow. Okay, so that's the setting. And we have 3 papers, 3 exams: physics, chemistry, and maths. Okay, so all of you have to give 3 exams in physics, chemistry, and maths, and all of you together have to come with the best way to study and ace this exam. So any ideas how we could do it?
Well, of course, we say we have our expertise already, and he probably does mathematics, and he does something else. You know, we just
how do you know?
Combine. We talk to each other.
Okay, you talk to each other. So, or else it could be like, I am the teacher, so I know that he expertises in physics, you expertise in mathematics, and you expertise in computer science, whatever. So this is one way, but let's go a little more behind. I could first tell all of them to learn all 3 of them, right? study maths, physics, chemistry, study maths, physics, chemistry. All of you study. I get the results, and I see what the results are, and I combine their outputs, right? And I say, okay, all of them have the same answers for the first question. Second question, all of them have the same answer. So this is ensembling. You're taking the vote. So that's the one way. Another way could be, I look at their outputs. I say, okay, this guy seems to be good at physics. This guy seems to be good at chemistry. And this guy seems to be good at mathematics. So I would, maybe next time what I would do is like, just give you physics papers. And just give you mathematics. And then just give you chemistry. And since they like it, they might do better again, right? So that's the intuition of mixture of experts. So I am the supervisor, so I have your results. And I also see how you do the first time, and then I give you papers according to how well they do. So that's it. Thank you. So that's the intuition. Basically, there's a teacher or the supervisor who basically looks at individual response from the experts and reassigns the input. So that's the whole idea about mixture of experts. So in this paper, the expert can be any algorithm. It can be a decision tree, it can be a support vector machine, or it could just be a neural network. So in this paper, we start off by building 10 experts, and we see how we get results from 10 to 100 experts. Yeah. So in this paper, the expert is SVM, and the teacher, who basically looks at the results from the expert, is basically a shallow neural network. Okay. So how does this algorithm work? So imagine I have some data point, all right? So, and they are like a binary classification problem, and you can see that, you know, maybe I could just give all the pluses to one expert and all the multiplications to another expert, but that doesn't really make sense because I don't know how it is. Initially, the teacher has no idea about his students. So maybe I will randomly divide my data and train it through an SVM. So I have this data, I train my model, and then I have another data set, I train my model. So the same data set divided into two. And then, so here is my data set down below. So I have the results saved already. So this is the first step. I train my support vector machines. That's the first step I do. And the second step I do is, I send the same data back into the neural network. So in the first layer, I have some 50 hidden units. So all my data goes to the first layer, which has 50 hidden units. And then, in my second layer, I have as many hidden units as my experts. So earlier in the slide we saw we had 2 experts, so I have 2 hidden units. And the third layer, I have a dot product layer. So where I combine the output of my experts, which I got from the previous slide, and the output of my layer 2. So yeah, so these robots. And finally, I squeeze this output through a single neuron. So this is what the gator does. And this is my output layer. So I get my x. So it says, okay, x is 0.9. So, and the other one is 0.3. So then I can say, okay, the x goes to the first class and the plus goes to a different class because of the probabilities. And then what I do is, this is the most important part, I take the output of my experts. So the weight, so the output of these experts will be some weights, and based on what weights they have, I will redistribute the data. So if the first data point has more weight for the first neuron and the second neuron will have lesser weight, I will give it to the first expert. And once I sort my data, I'll repeat this experiment 3 times. So usually you can do it how many more times you want, but your experiment converges within 3 iterations. So my cost function is the mean squared error loss. So basically, I want to minimize the loss between my predictions and the actual output. So that's the usual mean square error cost function. And the second one is the function for my expert. This is the multiplication part where I was talking the dot product layer, where I take the output of my neural network, which had 2 neurons, and I multiplied with the experts, the output of experts I had. Yeah, so that's the algorithm, that's it. So just repeating the whole thing, I divide my data into random subsets, train each expert individually, and keeping the experts fixed, I train my neural network, and I reconstruct my subset based on what my neural network says. So based on what the teacher says, okay, this guy is better in physics, maybe I should give this data point to this guy. And finally, I have a termination condition where I say, okay, if it's more than 4 iterations, if you have assigned your data 4 or 5 times, it's enough, just break. Or I can say, if your accuracy is like really, really stable now, I can terminate. So these are my results. So I have this data set, which was used in the experiment. It was called the forest data set. And by just using a single neural network, you can see the test error I had was like 16%. So it's quite high. Now let's just try that with a single SVM. So you can see the test error is only 13%. Now if we like have 10 SVMs and we give each SVM 10,000 examples, the test error is like 18%. So it's increasing. But when we do this mixture of experts kind of approach, your test error goes quite down and it becomes 9%, because each expert learns on a subset of data and it specializes in that. And this is my result. So you can see the training error or the training loss. So each color represents each iteration. So the blue one is the first iteration, then the green one is the second iteration, and the red one is the third iteration. And you can see that the gator, the loss obtained by the gator, is going lower and lower at every iteration, because experts are learning how to expertise in the subset of the data set. So that's the training loss, and that's the validation loss. So you can see that the loss goes lower as they tend to expertise. The experts tend to expertise, okay. And then this is one more example. So it's the same intuition again. So here, this is one expert, and you can see that on the whole data set, the loss is quite less. So if I give an expert, I train it, and I give it random subsets first, and I train it. So on the whole data set, it does quite bad. It does like 24% error, right? 20 to 24% error. And on the second iteration, the error increases. So why do you think that happens? Any ideas? Because it's expertized. So the experts have learned only on a subset of data. And now you're telling it to predict on the whole data set, it's going to do bad, because it's only seen some specific examples. And on the third iteration, it even does worse. So all the experts are basically learning to expertise, but on the overall data set, they do pretty badly. But when you combine their results, initially they do quite bad and they get better. So you can see individually on the whole data set, they do very badly, but when combined, they do pretty well. So you can see here on the third iteration, we observe an error of almost 9%. So the conclusion is that if you have this kind of divide and conquer approach, you can usually do pretty well, and you get quite good results. Now, since SVMs have this quadratic runtime complexity, you can basically launch off SVMs like in different cores and train them parallelly and combine the results. So they can scale linearly. So if you have like a lot of data sets and you launch 100 SVMs, and you can train your neural network really, really fast and get very good results. So that's it. Thank you.
Any expert questions? No? A single one? Yes.
Hi. Maybe can you share some details about what kind of data set you are using and whether it is what kind of kernel you use for the SVM, so to understand what is the setup?
Sure. So I tried my experiments in 4 data sets. First one was this forest data set, and the second one was CIFAR10, MNIST, and Anyway, I've not shown the results here, but these are different experiments. CIFAR10 SVHN dataset, and yeah, just for MNIST, CIFAR10 SVHN, and the forest dataset. And the thing was, this is a very good question, what were the kernel hyperparameters? In this paper, the authors don't mention it. So I did a grid search of like 30,000 experiments on a subset of dataset, and I found the best gamma and alpha parameters. And using that, I built my SVMs.
So these are squared exponential kernels, I assume.
Could you please repeat that?
These are squared exponential kernels, Gaussian kernels?
Yeah, they are Gaussian kernels.
Okay.
Yeah, RBF Gaussian kernels. Okay.
You can still ask questions afterwards. Cool, thank you. Another short break, and after we wrap up with the last talk.